having complement output input was similar to the complement. So other name is inverter. So we draw this NOT gate. This is the symbol of a NOT gate. Okay. By mistake, if you forget this bubble, then what it is called?
Buffer.
Buffer. So that's why this is a NOT gate or inverter. Okay. Here A is the input. Y is equal to A complement. Okay. Y is equal to A complement. What is inside this NOT gate? Any idea? Just like I said, when you give 0, I get 1. If you give 0 volts, I get 5 volts. If you get 5 volts as input, I get 0 volts as input. How do you see this? So what is inside this? What is inside this? How do you design this inverter circuit? Just take this NOT gate circuit using this grid complement. We are using actually this NOT gate is having single input and single output, except all other gates. All other gates are having two or more number of inputs, but only one output. In the case of NOT gate, it's not like that. Okay, so it is having single input and single output. It is designed by using transistor. Okay, if we use a single transistor, this is a transistor. What type of transistor it is? Transistor. Okay. So this is NPN transistor. One register here, one VCC. Okay, simply one simple circuit it is. Okay, you can take output here. Okay, even to protect this resistance here, okay, transistor you can protect this. Here, this is the A input, and this is the Y input. Okay, so this is the supply. Okay, you draw properly. Here, this is one resistor. So collector resistance RC, and I introduce this resistance in the base bar. This is RB resistance. Okay. Now, when you do 0 volts here, to operate this, to bias this, normally you give plus 5 volts here, plus 5 volts to bias the transistor. To operate the transistor, I'm giving plus 5 volts. I'm giving some logic input 0 volts here. Okay. So what will happen in this case? You know, this base to emitter junction voltage, how much it will be normally? This is the NPN transistor you said, no? So this is normally, if it is silicon, it will be equal to 0.7 volts like that, right? So it is less than this potential, this direct potential. Then, whether it functions or not, this transistor is in cutoff condition. Okay, no current is flowing through that. So it is simply whenever the input is equal to 0, A is equal to 0, the transistor goes to cutoff condition. Therefore, whatever the supply voltage is there here, that is available as output voltage. Some voltage is dropped across this and we get high voltage here. Whatever it is available here, that will be available. When you give low voltage, you got high voltage. When you give high voltage, say 5 volts here. So this, if you give 5 volts as input for your circuit, then what will happen?
The transistor turns on.
It's more than this 0.7 volts. Then immediately, okay, it starts conducting. So the transistor saturation condition. You know, both the junctions are forward biased, then the transistor goes to saturation condition. Like that we studied now. So whenever the input is high, the transistor BJT or bipolar junction transistor is in saturation condition. Okay, on condition. Then when it is on means the current is flow through this and it is simply acting like a switch, which means you can see that current goes to the ground. So nothing is available. Okay. So here when it is when it is okay. So you can see this. This is 5 volts, right? Just to see. This is acting like a we are considering this as a wire. So then it goes to the ground like this. So you cannot see any output here. When you give 5 volts, you get low voltage here. The output goes to go low. Okay. Just only two things you have to remember. When you give a 0 volts here, this is less than this constant volt, the transistor goes to cutoff condition. Okay. So then, so when you it is acting like an open circuit, then whatever it is available, you can able to see the output here. Okay, across this load resistance R. Okay, you can able to see the output here. Suppose if it is high voltage, the transistor is in saturation condition, it is on condition, then it is creating some path for the current flow. The current is flowing to the ground. So therefore the output is going to low. So these two conditions you have to remember. So this is the truth table of y is equal to A complement. So now you can confidently say that. Okay. When A is equal to 0, the output is high, and A is equal to 1, output is 0. So based on that transistor inverter circuit, you are saying this. Okay. So if you know these three circuits, okay, that is enough for you. Because this AND gate, okay, suppose if you want to design NAND gate, what is that you can have now? NAND gate is this. How do you get this NAND gate? NAND gate plus NOT gate. You know AND gate circuit, you know the NOT gate. How do you design using these three components? Okay. Similarly, NOR gate. NOR gate also you can design because you know the OR gate, you know the NOT gate, so you can implement them simply. Okay, using OR gate, using discrete components, you know. So using discrete component, this NOT gate also you know. So you can easily this is NOR gate, right? So this is a NAND. Okay, this is a NOT. These are universal OR gates. Using only NAND gates, you can design any big logic circuit. Using only NOR gates, you can design any big logic circuit. Okay, for example, I do one expression. Y is equal to AB plus CD. How do you design this? Using only NAND gates. Then simply we take as it is this. Okay, AB means I do A, this is A, and this is C. Another AND gate I am taking C, and this is A. Suppose here what gate I have to use?
OR gate.
Okay. Then we take this. So this is AB, this is CD, AB plus CD again. I am asking you to implement using only NAND. Whenever AND gate is there, bubble here. Okay. And whenever you put bubble here, you have to add one NOT gate so that it will be compensated. Whenever you put bubble here, just remember when AND gate is there, add bubble here and add this NOT gate. Here also NOT gate. Okay. When OR gate is there, you have to instead of putting bubble in the back side, you just put bubble here. Okay. And you added bubble here, no? Immediately you have to add one inverter here. So this externally I am doing. So nothing is changed. I have done this and this, right? So by doing this, here you can understand this. This NOT gate and this NOT gate. Can I replace this now? I can easily replace because double complement now. replacing this. So simply I can add this and this. Okay. And now this can be eliminated. This can be eliminated. I can add this and this. Okay. So you know this bubble OR gate is nothing but what? NAND. So you can easily replace this bubble OR gate with NAND. Like this, you can design any of the circuit. Okay, using if I give if anybody gives you this expression, this type of Boolean expression. So first what I have said to you, if AND gate is there, okay, the first step is AND gate is there, you just add bubble to this. Okay. And if OR gate is there, AND gate is there, add bubble and immediately you put NOT gate. Okay. OR gate is there, put bubble here. Okay. Then so that okay, you can replace whatever you have added here. Right? So these things you have to remember. Now we see the counter design. Are you perfect in flip-flops? Are you perfect in flip-flops? Have you studied the flip-flops concept?
Yes,
Yes,
ma'am.
Yes, ma'am.
What is the any one of you please tell me what is the importance of a flip-flop?
It is used as memory element in sequential circuits.
What is meant by sequential circuits? What is the difference between actually what are the important differences? Combination.
Memory elements are present in sequential circuits.
Okay, good.
That is a
Okay. So can I give examples for the combination circuits? All gates, adders, subtractors, componenters.
mux, demux.
Yes, good. What are the sequential circuits then?
Registers, counters,
Flip-flops.
Flip-flops. Oh, good. So flip-flops you might have studied very well. Okay. So we'll directly go to the counter design circuit. Okay. Or else I'll just refresh this. Or else flip-flop. Flip-flop or else flip-flop. Number one is 1 is equal to 0. Clock is applied. Then it is performing. R is equal to S is equal to etc. Whatever you get the RS is a non you have to introduce AND gates before that. Okay, so that you must remember when clock is applied, when D input is equal to 0, the same is available here. D is equal to 0, output is also 0. When D input is equal to 1, the same output. So that's why these D flip-flops are used in registers, in buffer registers. Okay, in almost all registers. Okay, and in ring counter, we use toggles, right? That is considered as base around condition. That is eliminated by using master slave JK flip-flop. Like that also you have studied, right? So this is a JK flip-flop. In this JK flip-flop, this is a simple loop, okay? So whenever you give negative edge triggering for the JK flip-flop, it triggers and you can able to see the output. When J is equal to 1, okay. This is very important. Before going to the counters topic, you should have some knowledge on this. But I guess I'm refreshing that. You know what I am refreshing. In the case of the JK flip-flop, the truth table, we can take the truth table like this. JK, this is Q. Here, clock signal activate. Okay. You just tell me when clock is 0, whatever may be this, whether it is 0 or 1, don't get condition, you will get, what is this condition you get?
No change.
No change. That is also known as hold state, right?
Yes, ma'am.
NOR latch. Okay. So consider that is a NOR latch. Okay, it is a no change condition. And the clock is not given. Okay, or else clock is level triggering is there in the case of JK clock. So then also you will get no change condition. When clock is positive going edge, then also you will get no change condition. When clock is negative going edge, that means you know this is a clock signal. Okay, so if the flip-flop triggers during positive going edge, consider that as positive edge triggered JK flip-flop. Okay, positive edge triggering. You can call. So instead of taking this so much time, okay, just it is during only positive going edge. During this leading edge, if it is triggering the flip-flop, you can consider that as positive edge triggering. Okay, if it is triggering during this negative going edge, we can call that as negative edge triggering. Suppose if it is taking complete pulse, then we can call that as a level triggering. Okay, this level triggering is used in master slave JK flip-flop, and most of the cases in JK flip-flops we got to use this. Now for this negative edge triggering, okay, for 0 0 condition, 0 1 condition, 1 0 condition, you can able to see all the. Whenever J is equal to 1, the flip-flop sets as, when J is equal to 1, the flip-flop resets and stores 0 bit. Just remember these things. And when both inputs are 0 with no change condition. And one more important last condition, when both inputs are when both inputs are 1 1, what is the condition?
Toggle.
Toggle condition. What are basics of this toggle condition in the design of the counters? Okay, so simply you can compare this method. Okay, so when both inputs are this condition is important for me. When J is equal to 1, K is equal to 1, flip-flop output toggles. That means to explain its operation, always you are assuming the previous condition, right? So the previous condition of the flip-flop, it might have stored a 0 bit here previously. So that is Qn minus 1, that condition A. Now, what is this in the next condition? What is J is equal to 1, K is equal to 1, what do you get here?
1.
That means toggle condition. Next condition, what do you get this plus 1 condition? Next state. This is the previous condition.
0.
Like this it happens. This continuous toggle process is there in JK flip-flop, and we are, because if you observe the circuit of this JK flip-flop, okay, so I got this. So this. So we extend this and here this one. So this is the J input. This is your unit input. Okay, this is your clock signal. We don't give clock signal directly like this. We use differentiator here. Okay, means differentiator means capacitance is there, resistance is there. Okay, so we do the differentiator circuit we do here, and we introduce one diode here. Then it can allow, okay, to negative spikes will get no. So this diode can allow only negative spikes here. So this diode can allow only negative spikes, so that this flip-flop will be triggered. Okay, so whenever the negative spike occurring, then based on these inputs you can explain its operation. When J is equal to 0, K is equal to 0, again you will get previous condition 0, 1 means the same results you will get. When J is equal to 1, K is equal to 0. For this condition, you tell me what is happening in this JK flip-flop.
Set state.
Very good. Set condition. So you can able to see clearly what is this condition and all. When both inputs are 1, 1, so what is the status of this flip-flop?
S is 0 and S 1.
So toggling occurs based on the previous condition. 1, 0 is there means you get 0, 1. And this is continuously series. Feedback connection is there, no? So for that, so we can, if you keep this 1, 0 as it is, okay, then 1, 1 as it is, continuously toggling occurs. So that considered as one is around condition that can be eliminated by using master slave JK flip-flop. Okay, so this condition, whatever maybe, okay, so in the design of a synchronous or asynchronous counters, we are making use of this last condition. Okay, so just observe this condition JK. Okay, so next one is, this is a master slave JK flip-flop. So in master slave JK flip-flop, clock is directly connected here and clock is inverted and connected here. Okay, so this is actually, if it is a NAND latch, I told you already we have to introduce this NAND bits. Okay, so here one is acting like a master and other is acting like a slave. Just the slave copies the master information. Only based on this clock signal, you are controlling its entire operation. When clock is made high, this is active, and based on this input, suppose J is equal to 1, K is equal to 0, then it is set condition. Okay, and immediately we can put this low, then this will be active. Based on that, whatever this is, so even though there is a feedback connection, you can able to see all the condition properly. That's why using master slave JK flip-flop, we can eliminate that trace around problem. We can able to see the, otherwise in the trace around condition, we cannot predict the output state. Suppose continuously toggling for single clock pulse means, okay, for example, if you connect LED there, so you cannot predict the output status, whether if it is glowing and stable, then you can say consider that as it is setting, or if it is off means you can consider that as resetting, it is 0. So if it is continuously blinking means you can consider that as a race condition. So in most of the exams, you will have this question actually, what is race error problem, how it can be eliminated by using master slave JK flip-flop. We are just concentrating on this feedback. Even though there is a feedback, by this clock signal we are controlling. Just go through the theory of this. Okay. Now we'll see the counter operation. Okay. We'll go to the counter counters design. What are the different counters you studied? Have you studied counters topic?
Yes, ma'am.
What is the importance of the counter?
To count the number of clock pulses.
It counts the number of clock pulses, which I will explain, right? There are different types of counters. We have a synchronous counter based on the clock signal applied. We can classify them asynchronous and synchronous, right? So in the case of asynchronous counter, it is very easy for us to understand and to design the asynchronous counter. Then why do you prefer the synchronous counter?
Faster open than asynchronous.
Speed of operation. Okay, because in the case of asynchronous counter, just observe this. This is actually counters are designed by using flip-flops. That too, JK flip-flops are T flip-flops. Okay, I am using a 3-bit counter, 3-bit triple counter. Just observe this. Here, clock signal is given to the first flip-flop. Okay, and it is having some JK inputs. The output of this, consider this is Q0, is connected as the clock for the next flip-flop. The output of this, okay, consider all JK inputs, this is J inputs. The output of the second flip-flop is connected as the clock of the next flip-flop. So this type of clock, okay, if you give to the flip-flops, consider that as asynchronous. That means when the first flip-flop triggered by the, and if you get the output, then only this next flip-flop is triggered. You get the output, then only this flip-flop is triggered. That means there will be some propagation delay, no? So that's why, so the speed of asynchronous counter operation is very less compared to the synchronous counter. Even though some of the, because design complexity is less, we prefer to use in some of the applications this asynchronous counter. Okay, and in the case of synchronous counters, it is not like that. Simply we use, okay, so at a time you can give clock signal to all the flip-flops. That is a synchronous counter. Okay, and one more important function. Okay, can you count random sequence using counters? Suppose if I want to count, this is up count, right? And if you take this as 5, 4, 3, 2, 1, this is a down count. Or else 1, 3, 5, 10, 2, this is a random sequence. So any type of sequence can be, okay, designed by using a synchronous counter. Okay, so that's why we prefer to the synchronous counter. Any random sequence if you do, based on that sequence, it can count the sequence. What is a practical application of the counter? What is a practical?
Practice.
Ma'am, used in timers.
Traffic signals. In industries, when they place this counter, digital counter there, some lakhs of component, they are preparing some products, no manufacturing. After manufacturing, the products is standing there and counting it. Is it difficult process or simple process? It's very different, no? So by placing this counter there, whenever that product is falling on that, it can give one count. So that you can count that. So no need of a person stand there and count them. Okay. So digital counters are placed in the industries to count the industrial finished products, or else we can place this in pilgrim places. How many people visited that temple, like Tirumala Tirupati Devasthanam? Okay, so every day, so several people, some millions of people are visiting, no? So they place a counter there. Whenever you touch your feet touching there, so it takes it as a count. Okay, So by putting that pulsar switch, by pressing that pulsar switch, it can increase the count. So many applications are there. Okay, in many applications we are using these counters, and it is also used in computers to control its processing and all. Now we see the design of asynchronous counter. In the exam, they will ask you design a mod 8 asynchronous counter or mod 5 asynchronous counter. So how do you design this? So we will see that for the design of asynchronous counter, we just use this expression n is equal to 2 to the power of n. Okay. This is the modulus, and this gives us a number of flip-flops. Suppose if I ask you to design a mod 8, okay, mod 8 means I am putting, this is the, suppose consider this mod 8 counter. If I ask you to design a mod 8 counter, so how many flip-flops are required?
Three.
Like that. So 8 means I put this here 8, and this is to the power of 3. So base of this, just we can see now, so that we can find what is the, okay, we can equate the bases and we will get this, right? So similarly, if I do design mod 16, okay, design a mod 16 counter, and what is its counting sequence? And how many flip-flops are required?
4 flip-flops are required.
4 are required.
0
okay.
to
This, okay, so you can say that this is mod 16, just put this 16, and this is 2 to the power of n, and now this is 2 to the power of 4, and this is n is equal to 4. 4 flip-flops are required. So what is its counting sequence? 0 to 15. 0 to 15 means we can write that the counting sequence of this flip-flop is equal to
0 0 0 to triple double 1 double 1.
Okay, whatever may be this, okay, whether it is mod 16 or mod 10. If it is a mod 10, what is its counting sequence then? 0 to 9. 0 to 9. If it is a mod 8, 0 to 7.
0 to 7.
12,
0 to 11.
mod 100,
0 to 99.
Okay, this expression is enough for us. N is equal to the power of n, where n represents number of flip-flops, capital M represents modulus of the counter. Okay, so just to use that expression for the design of counters. Now, asynchronous counter. I'm designing a mod 8 asynchronous counter. What is the other name for this?
Ripple count.
Yes. Another name. Can I call this as a 3-bit counter?
Yes, ma'am.
Okay, so you have to think of what they have asked in the design of this counter, whether they have asked repeat counter, mod 8 triple counter, mod 5 counter, or asynchronous counter, or synchronous counter. So, and using D flip-flops, they ask are using JK flip-flop. So everything is important for you. Okay, so in the design, you have to concentrate on that. Okay, so now I am designing this mod 8. Okay, so here you please take this JK, 3 JK flip-flops are required, right? Mod 8 means, so you write that expression, okay, n is equal to 8, and here n is equal to 3, so 3 flip-flops are required. That too, we have to use 3 JK flip-flops. Okay, simply take the 3 JK flip-flops. And what may be its counting sequence? 0 to
7.
So that means we have to see that we should count from 0 to 7 and you have to use 3 JK flip-flops, right? And this is asynchronous counter. That means clock signal should be connected to here. You are giving clock signal here and JK inputs, all JK inputs should be connected to logic high. This is very important. Okay, all JK inputs should be connected to logic high. So take JK inputs. This JK inputs connected to logic high, right? So here this is JK. The output of this, consider this is output. Q0 bar is not required for us in the case of asynchronous. This is Q1 bar. So Q1, okay. This output is connected to the clock of this next clock. The output of this is the circuit. Okay. So try to understand its operation, how it is giving. Okay, the result. How it is giving the result. Now I'm extending its operation. This is Q0, right? Extend that to Q0. Okay. And this is Q1, right? I want to see this result in my actually output indicators. So that's why I'm extending its operation, this Q1. So every time I can give them to the light diodes. Okay. And I connect this to the peer. It's very important. In counters, this clear signal is playing very important role. Okay, so compulsory you have to use this clear. Okay, I'll give you the concept. So when clear is made high initially, you can reset all the flip-flops. We don't know what is stored in those flip-flops. So that's why initially you have to set clear high. Then you can reset all the flip-flops. Later, you pay clear is equal to 0. So once if you give clear 1, later you set that to 0. Then start giving the clock pulses. So and one more condition, you are giving all the JK inputs logic high. Okay. Now one by one, if you give clock pulses, okay. First you give 0. Okay. Then what may be the result here? You can able to see. The clock input is equal to 0. What is the inside operation of this counter? 0, 0, 0, 0, 0. Very good. Now I am applying one clock pulse. Of course, negative edge triggering I am giving. Okay. Then what happens here?
Q0 is 1, Q2, Q1 and Q2 is 0, 0.
Very good. So she said, so this will become 1. What will be the reason?
It toggles the output when clock pulse.
First clock pulse is applied, first clock output toggles. Then 0 becomes 1. Okay. So actually this is a clock signal, right? So during negative going edge, okay, actually this is 0, this is 1, and this is 1, this is 0. So here we are calling this as a negative edge triggering. Okay. So 0 has become 1. That negative change is applied as the clock for this. So this negative change, okay, that negative change is applied as a clock for this. Okay. Here, but it is a not negative change. Sorry. Here you have to understand one thing. 0 has become 1, right? That is a positive change. That positive change is applied to the next flip-flop. Is there any change in the status of this second flip-flop?
No, ma'am.
Because I said whenever you give positive going edge, the flip-flop does not function. Okay, so that's why the output is no change. Does not just no change output. It holds the previous state only. So it remains 0 only. Okay, so when clock is here, This 0 is applied here, no? Nothing is changed here. That's why whenever you give the first clock pulse, the first flip-flop output is toggling and you are getting, instead of 0, you are getting here as 1. Okay? 0 has become 1. You just remember this. This is a positive change. Because of that positive change, this is not changing. Okay? So then so the entire functioning of the flip-flops based on the clock signal. Okay, so now I am giving the second clock pulse. Okay, by making clear is equal to 0, it is happening now. Okay, now if I give second clock pulse, if I press that pulsar switch, then what will happen?
Q1 is 1.
Yes. So immediately, whenever the flip-flop clock pulse strikes the first flip-flop, always this first flip-flop output toggles. Just remember that. That means earlier it is 1, now the result is 0. Okay, so 1 has become 0. What is this change? 1 has become 0, negative change, right? This negative change is applied as a clock for the next flip-flop. Because of that reason, the second flip-flop toggles. Okay, so that means this 0 becomes 1 now. What is the end result? So you can able to see here 0, 1, 0. Initially, you have seen 0, 0, 1. Now, what is the result you got? 0, 1, 0, right? So, if you give third clock pulse, if you understand this concept, you just tell me what happens.
0, 1, 1.
0, 1, 1.
0, 1, 1. So, similarly, it continues its counting sequence, right? So, the logic behind this is, okay, suppose if I give you third clock pulse for this, third clock pulse I give, then previously what is that result actually for the second clock pulse? The result is like this, no, 0, 1, 0. Okay, third clock pulse strike means this 0 becomes 1, right? 0 becomes 1 means what is this change? Positive change. That's why it remains same, 1. And this, when it is not changing, same, no, that's why nothing is changing in the next flip flop. That's why you can able to see the result as 0, 1, 1. Okay, when fourth clock pulse is there, then again, okay, this 1 is there, no, so this 1 will become 0. Always that's the first flip flop output toggles I said. As 1 becomes 0, because of that negative change, this also toggling. So therefore, here, this 1 is there, no, that will become 0. That will become 0. And that 1 has become 0 means that is negative change. That is applied to the third. So then that flip-flop output toggles. Okay. So you can able to see this as 1 here. So this entire thing appears as 100. Okay. You didn't understand this concept. Simply, okay, you take the truth table, and start writing this. This is the clock signal. Okay. And this is Q0, Q1, Q2. So when clock is 0, I said it is 0. Okay. When clock is made high and it is 1 first clock pulse. So then first clock output toggles I said. Okay. When second clock pulse is there, the result is simply I am writing binary numbers. Just observe this. 3 is there means this is 0, 1, 1. 4 is there means 1, 0, 0. 5 is there means 1, 0, 1. 6 is there means 1, 1, 0. 7 means all ones. 8 means, should I take that 8?
No, ma'am.
If you take that also 8, you have to show that as all inputs will be 0. Right? So last condition also you take and show that as 0. So you can see this here. When first flip-flop output toggles, no, 0 has become 1. Because of that, nothing is changed here. So in the second clock pulse is given, then 1 has become 0. Okay, this is a negative change. Okay, because of this negative change, next flip-flop is toggled here. But this is a positive change, that's why nothing is changing here. So like that, you can explain. Here, first flip-flop output, just observe this. 0, 1, 0, 1, 0, 1 you can have. That means always the first flip-flop output toggles because of the clock signal. And because of that, J is equal to 1, K is equal to 1. Don't forget this. We are giving clock signal, negative edge triggering, and here J is equal to 1, K is equal to 1. Okay, the first flip-flop output toggles continuously here. Okay, so based on this clock signal. That you have to remember compulsory. All data input should be connected to logic high and clock signal should be given. Okay, for the first flip-flop. The output of the first flip-flop is connected as the clock for the next flip-flop. The output of the next flip-flop is connected as a clock of the next flip-flop. Like that it continues. Okay. And initially what I said to you, clear should be given. Okay, clear should be made high. This is actually CLR. Okay, clear should be made high. CLR I am showing. Okay, so whenever clear is made high, whenever clear is made high, we can reset all the flip-flops. This is very important point. You have to reset all the flip-flops, by making clear is equal to high. Later, whenever the counting operation starts, you have to keep the clear is equal to low. Then give the clock signal. Okay, so like this 0, 1, 2. Okay, based on that it can perform its operation. You have to draw that logic circuit, you have to write the truth table, and you have to mention all these points. And sometimes in the exam they will ask you what is the timing diagram of that. So for timing diagram, okay, so here this is the clock signal. Okay, so Q0, Q1, Q2. Okay, suppose 0, 1, 2, 3, 4, 5, 6, 7. Okay, so we got this as 0, 0, 0, 0, 1, 0, 1, 0. Then that is you are mentioning, right? So in gate entrance point of view or in the end entrance end exams, they will ask you these results. Okay. And they may ask you draw the timing diagram of that. So first you have to draw the clock cycle like this. You have to draw this. Okay. And suppose this is 1, second, third, okay, fourth clock pulse, fifth clock pulse. Then during just observe this. This is a Q0. Like this you can take Q1, Q2, Q3. Q0 is for the first clock pulse, okay, it is 0. Okay. And during the second clock pulse, what is its see this. First you take this for the 0 clock pulse. Okay, and for the first clock pulse, almost okay, for the first clock pulse, it is 1. Then I am taking this as 1. Second clock pulse, it is 0. Third clock pulse, it is, so like that, you just observe this. Okay, so first clock pulse, what is the result? Logic high or 0? So like this continuously, you can able to draw this. Similarly, for this Q1. So for the first clock pulse, initially it is showing like this. Forget about this, just concept. So 0, 1. Okay. Now this is 0, 1, 1. So initially it is 0. Then it is for the second and third it is 1, 1. So like that you can consider. I have not drawn properly, but you take that. That the logic behind this timing diagram is just simply you have to consider properly. You have to consider. Otherwise, I will draw this. So you can consider from here onwards. So here to draw the timing diagram for this, you have to take the clock signal first. So proper clock signal we take like this. Okay, and mention. Okay, so this is up to here. It is 1 we consider. This is second clock pulse. This is a second, a third. Okay, so you can consider this. Okay, and for this, suppose I am taking this, but during negative going edge only it functions, no. So only I am concentrating here. Only I am concentrating here. Okay, so you extend its operation up to 7 clock pulses. Then for Q naught, okay, you can take this. For the first one it is 1. I am taking this is, okay, here onwards you take, here this is 1. Okay, so then I am taking this is 1. Then for the second clock pulse it is 0, and whenever it is going, okay, then immediately it is changing its leading negative going gate. It's again leading negative going gate. It is changing its 0 becomes 1, 1 minus. So like that, you concentrate on this. Proper diagram is important for us. So this is the logic actually. See this. So this is 0, 1, 1. So then initially for the 0. Okay, then immediately during negative going gate 1, 1. Okay, then immediately I can draw this up to here. Okay, then immediately it is changing 0, 0. So up to this 2, then 1. Like that you can draw. Okay, similarly for this Q3. For Q3, how do you draw? 0, 0. Okay, so like this you can draw that. Okay, 0, 0, 3 up to 3 clock pulses. Then immediately there will be change. So you practice this timing diagram also in the exam. Okay. This is compulsory question. That's why they might have kept this webinar for you people. Okay. And one more important topic now, mod 5. If I ask you to design a mod 5 counter, now the question arises here. So how many flip-flops are required and how to design this mod 5 counter, asynchronous counter?
3 flip-flops.
3 flip-flops are required.
Okay. So I'm taking 3 flip-flops. Okay, if I take 3 flip-flops, what is its counting sequence?
8.
0 to 7.
But what is the mod 5 counting sequence?
0 to 4.
0 to
4.
That means the remaining state should be skipped off, right? So after 4, it should not count. Okay, that means whenever the 5th clock pulse is given, you have to reset the flip-flop. Then it starts counting from 0 to 4 only. So that logic you have to apply here. So for this, what you have to do, you take 3 JK flip-flops, 3 JK flip-flops. Okay, you take 3 JK flip-flops. With the same gate you can connect like this. Okay, so all JK inputs should be connected to logic high. I said no. So connect all the JK inputs should be connected to logic high. This is compulsory. This is the first point. Okay, so first connect all JK inputs. Okay, to logic high. This is JK. I said JK. Otherwise, if you forget, you won't get marks for that. Okay, so this is the clock signal. Okay, suppose if you left your edge triggering, just consider. See, here I am using what I said to you. Clear is also important for us. Clear is important. Okay, if I do just like this, Q0, Q1, Q2, it can count from 0 to 7 continuously. But somewhere I have to reset this. For that purpose, I use one simple OR gate here. Okay, and I give clear signal here. I mention this as clear. Okay, and I connect this to one AND gate here. One AND gate. Suppose if I extend its operation, I am connecting this to here. Okay, so connecting this Q0, Q1. So I have to do something here. If I continuously, if I put where I have to reset here for the 5th clock pulse, it should count from 0 to 4 only. Okay, what is the 5th clock pulse? Whenever it is there, what is that? We'll get 101. Here, I shouldn't get this 101. Instead of getting 101, I have to get 00. That means here for 0, I put 1, not get here. And directly get connect here. Okay. So what you have to do initially, you are making here is equal to 1. So either it may be 0 or 1. What is the output of OR gate? Is 1. Then you can clear all the flip-flops. Okay. Then whenever you give the clock signal, based on that, okay, you will get the counting sequence from 0, 0 to 100. Okay. When 101, when fifth clock pulse, if I give you fifth clock pulse, or if I press that pulsar switch, fifth clock pulse, then what will happen? Instead of getting 101, okay, otherwise 101 comes no. So this 0 is the output, no, that 0 I'm giving here. So this is 1, this is 1, the output of this is 1. Okay. So initially I said I gave clear is equal to 1 and I have put 0. Then only it is possible, no, for the counting process. For when it is 0, it is counting like that. Okay. Initially I made clear is equal to 1 and started. Okay, I reset this all the flip flops. I got okay 0 0 initially. Okay. Then I put the 0 and start giving the clock pulse. Then it starts counting. Okay, this is a 0. But indirectly by using this external circuit, okay, once again I will tell you. So by using this external circuit, okay, I am making this as 1. Okay, therefore the output of this mod 5 counter just stops there. Okay, it's just the whenever 50 clock pulse is there, it shows 0 0. Once again I draw this and I'll clearly explain to you. Okay, what I am saying, so suppose if just this is a mod 5 counter I am saying. Mod 5 means, okay, it should count from 0 to 4 only. Whenever the, okay, fifth clock pulse is there, so you are getting 101. I am resetting that to 00. I am saying. That purpose, what I have to do is just initially I gave clock signal to the circuit. Okay, I didn't change anything here. Connected to logic, right? Only the external arrangement. Earlier, clear is made high.
Madam, Sai Teja. Please mute yourself, Sai Teja.
ఫోన్ చేస్తే ఆయన లిఫ్ట్ చేసి ఇంకా అంతే అనిపిస్తుంది. నీ దాని దగ్గర కాదు, ఫోన్ నుంచి మాట్లాడా
Sai Teja.
అవును సప్లై కూడా
Sai Teja. Okay. Sorry, madam. You can continue, madam.
Okay. What I am saying, in the case of mod 8 counter, simply I made clear is equal to 1 and I have reset all the flip flops. Then I have put 0 and I gave clock signal. Based on the clock signal, it started counting. Okay. Whenever clear is 0, then only it starts counting. Okay. here also I get only, okay, so by using one external arrangement, what is that? Simply I connected one OR gate. In different mode also we can connect actually, but I am saying for understanding purpose, I am using one OR gate here. Just draw one simple OR gate. Clear signal is this one, and you have to use one AND gate I am saying. So you have to reset this 101. So whenever 101 is there, you have to reset that to 0, means wherever 0 is there, you just connect this and use one NOT gate here. Okay. So, and this is 0 inverted. 0 is inverted and connected here. And this 1 also I connected here. And you can connect this 1 also here. So that the output is 1 here. Okay. So initially I made clear is equal to made high, and I kept this to low now. Okay. I kept this low means, so initially when clear is made high, whatever may be this condition, okay, whatever may be this condition, I am getting this as 1, and I can reset all the flip-flops initially. But, okay, when the counting sequence started, I have kept this as 0. Okay, I have kept this as clear is equal to 0. Now, based on this only, you can get either 0 or 1 here. Okay, now the output of this AND gate is 3 input AND gate is high. So, any one of the inputs of this OR gate is high, then the output of the OR gate is high. That's why I can reset all the flip-flops. Though it is displaying 101, so you cannot get the result as 101. It displays only 000 only. Okay. Similarly, if you want to design a mod 10 counter, so what may be the circuit diagram? So now all of you try to design a mod 10 counter. Tell me how many flip-flops are required to design mod 10 counter?
4, ma'am.
4. Suppose if you consider 4 flip-flops, okay, what is its counting sequence?
0 to 15.
0 to 15. Okay. But I want, what is the counting sequence of mod 10 counter?
0 to 9.
Okay. That means after 10, it should not read. That means it should not read this 1010. So you have to reset this. Okay. So afterwards, it should not read this. Okay. That's why you are simply taking this. Okay. So while designing a circuit, okay, mod 10 counter, simply you are taking all 4 JK flip-flop, same circuit, so nothing is new for us. 4 JK flip-flops I am taking. Just take this JK inputs, JK, JK, JK. So all JK inputs be connected here. Okay, this is, don't forget this. Okay, all JK input should be connected high, and clock signal should be given to the first flip flop. Clock signal should be given to the first flip flop. This is the clock. Clock signal, and the output of this is connected as the clock here. Output of this. So this is Q0, this is Q1, this is Q2, right? So now what I have to do, just tell you. So clear is mandatory for us, right? So clear, I am taking from this actually clear signal, and here you extend this Q1, this Q0, this Q2, this Q1. Okay, so I said it is counting from 0 to 9. You should not count this 1010. That means 1010. That means wherever zeros are there, I have
Not gate.
yes, zeros not gate. So that's what I want to tell you. Okay, so 0 is there means you put this as inverter, and this, so simply use 4 input AND gate and connect this. That's it. Okay, initially you are making clear is equal to 1 and reset all the flip flops. Afterwards you are putting this as 0, no? So everywhere 0. Then it starts counting. But indirectly by using this arrangement, so I am putting this as 1 now, right? The output of this AND gate is 1 means one of the inputs of the OR gate is high. Then this is clear is made high. Okay, so this is the logic actually. This logic you apply where you suppose sometimes chip enable or their active low inputs are based on that it will change. Okay, but this is the logic. You should be able to explain this logic. Okay, like this any counter you can design, any asynchronous counter. If it is a mod, if I ask you to design a mod 12 counter, then what do you do? Anyone of you? Mod 12 counter should count from 0 to 11. It should not count this 12. That means what is 12?
11002.
That means I have to put this. Okay, so 1 1. Directly I can connect this 1 1, right? So this is 1. Okay, I can do this 1 directly. Okay, this 0 is water and connected. 0 is water and connected. And this is direct, right? So this is 1, this is 0 0, right? So this is the circuit. Just it can count from 0 to 11. This is the mod 12 counter. So like this, any counter you can able to count by using this concept. Is it okay for you or?
Yes, ma'am.
Yes, suppose if I ask you a small question, randomly I'll ask you. Otherwise, anyone of you please tell me. Mod 3 counter, how many flip flops are required? Mod
2 flip flops.
flip flops are required. Okay, so for this, simply I take this, right? 2 flip flops, JK inputs. Flip flop, just by shorting J and K, it is acting like a T flip flop. No?
Only T, 1 input.
Yeah. So just by shorting this J and K, so it is acting like a simple. It is acting like a simple flip flop. You can construct this as a T and put that as 1. Okay. Suppose if I ask you to design mod 3 asynchronous counter using T flip flops, then simply put that the clock signal is given here. Okay. Then clock is connected here. Then this things should be connected to logic high. Mod 3 I said it should count from 0 to 7. 2 only. actually 1 1. It should not count 1 1. That means it should count from 0 to 2. It should not count this 1 1. Okay, what do you do then?
AND gate is applied to T output.
That means, so initially you are using this clear, right? So this is the clear. Okay. So initially we said clear is made high, and we have kept that as 0. So as it is, we can take this and connect to the AND gate directly, and this is 1. Okay. So one of the inputs of this one means this is 1. We can reset all the filters. We can count from only 0 0 0 1 1 0. Whenever 1 1 is there, it just reads like this. So you can mention clock signal here. Okay. 0. This is from 1 2 3 and so on. Okay. So like this, you can extend its operation in future. Okay. Now synchronous counter design. So for this synchronous counter design, you should aware of the K-map technique. Have you learned actually this K-map simplification now?
Yes, ma'am.
Yes.
Very good. If you know K-map simplification, if you know the excitation table of the JK flip-flop, you can easily design this synchronous counter. These synchronous counters are used to count even random sequences. In the exam to this you people, they will give random sequence. Even you should able to count that random sequence also based on that. Okay. So now we'll see the concept of the synchronous counters. Design of synchronous counter. Design of synchronous counters. Let us see the first one, a simple mod 8 synchronous counter. Okay. So in this mod 8 synchronous counter, how many people have same? Okay. But we are giving clock signal in a different mode. Okay. So you should not use like this simple, it is not a simple thing. Just you have to consider, okay, mod 8 is, what is the first step of this design? You just to see that it is a mod 8. Okay, it is a mod 8. How many flip-flops are required? You should understand. 3 JK flip-flops or 3 T flip-flops are required, right? This is important for us. And what is its counting sequence 0 to 7? We should know. Third one, you should know the truth table of JK flip-flop, and from that truth table you should know the excitation table. Okay, so this you should know. Next step, from the excitation table, okay, you are preparing, you are writing the expressions for, okay, what is the expression for J, what is the expression for K, like that you are finding J0, K0. 3 flip-flops means you will get J1, K1, J2, K2. Okay, you have to get the expressions in terms of Q0, Q1, Q2. These expressions you have to find out. If you know these expressions, you can able to design the circuit. This is the design procedure. Okay, design procedure. So now we'll see that how it will be. Mod 8 counter I said. How do you design this mod 8 synchronous counter? First you have to take JK flip-flop truth table. Okay, 3 flip-flops anyhow, but this third step I am directly drawing. JK inputs, output is there. 0 0 condition, 0 1 condition, 1 0 condition, 1 1 condition. For this JK, no change, and this is a reset condition, this is set condition, this is toggle condition, right? You know, this is a toggle condition. Suppose Qn is there means this is Qn minus 1 complement. Toggle condition. Okay. From this truth table, you are finding excitation table. This is the truth table of a JK flip-flop. Now, how do you prepare the excitation table? You can by heart also. That's why I am telling. Okay. So, what is the present state? What is the next state? What are the inputs for the JK inputs? This gives us the excitation table. Suppose present state is 0. Next state is also 0. Tell me what is the next JK inputs condition?
J is 0, K is don't care.
J is equal to 0, first condition. Okay. Even this is 0 and this K is equal to 1 also, you get the same result, no? And K is also 0, 1 is also, this is 0, no? That's why you get the same. So that's why she said this K is equal to don't care. Okay, you can put this K is equal to don't care here. Okay, J is equal to 0, K is equal to, okay. Now, when present state is 0, next state is 1. Now you tell me.
J is 1, K is don't care.
Present state is, okay, present state is 0. Now you tell me what is this JK inputs?
1x.
0 has become 1. When it possible, when both inputs are 1 1, you know this, right? And even K is equal to 0 also it is possible. K is equal to 0, J is equal to 1 also it is possible. Set condition, right? That's why we give this as it is and we give here as don't care. This one is don't care. So I'm putting this as don't care and leaving this as 1. You understand this or not?
Yes, ma'am.
This is a present state. Okay, that means the previously stored bit is 0. Next state it has become 1. When it is possible 0 has become 1, you know that no, in the J is equal to 1, K is equal to 1, the flip-flop output towers will get 0 and 1, right? That's why it has like that. That's why I have kept this as 1 initially. Even 0 has become 1 means when K is equal to this is very important. That's why in the exam also you should not forget. Okay, when both inputs are 1 1, we will get this condition. Even K is equal to 0, J is equal to 1 also you get the same condition. That's why I am telling. So here 1 0 are there, no? So for that we can place this as don't care. That's okay. Similarly 1 0. So any one of you please tell me 1 has become 0. What are the JK inputs?
0 1 and 1 1.
First one is toggle. Always remember this, right? Even K is equal to 1, J is equal to 0 also you get this result. That means the flip-flop resets and stores 0 bit, right? So now this can be replaced as don't care. This can be replaced as don't care. So I'm replacing this as don't care and I can eliminate this, right? Now both inputs are 1 1. Then
Don't care, comma 0.
that means no change now. 1 1. See this. It is 1 1. toggling condition you can have, right? No, not like that. Don't get confused. Okay, with this also you will get confused, but you should know this concept actually here. So when previously the stored bit of this is okay. Previously the stored bit of flip-flop is 1. Next state also you got 1. No change condition, right? No change means what is that you can write here? No change means, can you put this as 0, 0?
Yes, ma'am.
When it is 1, when j is equal to 1 also we get 1, 1. When k is equal to 0. So that's why you can put this as don't get condition. And if this remains as 0, so this as don't get. So you should not forget this excitation table. Okay. So what I am saying, suppose this is a flip-flop. Okay. So this flip-flop previously it is stored 0 bit. Okay. So that means this Q naught is equal to Q is equal to 0 and this is equal to Q bar is equal to 1. Okay. I am giving for this JK is equal to to explain this flip-flop operation always you have to assume the previous condition, right? So previously the stored data is like this. Okay, now I am changing. I gave this as 1 and this as 0. Then immediately what is the result you can get? This is a previous state. Okay. Otherwise, this is a present state. Okay. What is the next state for this? What is the next state when you give the inputs like this? Tell me. Hello.
Set state.
State. Okay, 0 has, that is a state. In present state, it is showing it as 0, 1, right? That Q is equal to 0. Okay. But in next state, what is that? Actually, set state. Okay. 0 has, that's what I am saying. You consider this is the output, present state. Next state means Qn plus, this is Qn and this is a Qn plus 1. Okay, how this is changing? Present state is 0, next state is also 0, means it is like a no change condition. That's why we have put jk is equal to, j is equal to k is equal to 0, just 0, 0. And even the next state is 1 means even k is equal to 1 also it is 0. That's why, so did you understand this or not? One of you please come forward and explain this. Why I got this excitation table, how I got this, so that your friends will understand clearly. Hello. Did you understand this or not? This excitation table is important for us.
Yes, ma'am.
Others?
Yes. Yes, ma'am.
Okay. So don't by heart this. It is easy for us to remember. Okay. So I am telling that the flip-flop previous condition and present state, this PS is represented as present state here. Okay. And NS is represented as next state. Present state is 0, next state is 1 means, so when it is possible in the case of flip-flop, when both inputs are 1, 1, toggling is possible, no? So that's what they have represented like that. Okay, so you please concentrate on that excitation table, try to understand that. So if you understand that, the entire one will be finished. Okay, so that is playing very important role in this synchronous counter. Okay, I am asking you to design a mod 8 synchronous counter, right? So for that, you have to prepare the excitation table. Okay, so you know the basics. So, but with that you are preparing the excitation table. So you have to prepare this as present state. Okay, you know there will be some 3 flip-flops, right? This you know because of this. So that means this is Q0, this is Q1, this is Q2. So you can state this as Q naught dash, Q1 dash, Q2 dash. Okay. So this is a present state and this is the next state. Later you are finding three flip-flops, right? This is J2, K2, J1, K1, J0, K0. Like this you have to prepare the truth table. Okay. So now you just tell me how do you write this truth table? 0 to 7, right? So I'm writing 0 to 7. 0, 0, 1, 2, 3, 4, 5, 6, 7. You should write this. Okay. Parallelly, one of you should prepare this. Okay. Present state is 0 means what is the next state here? So I'm writing this next state. Next state of this is 0, 1, 0.
0 1 0
This is
0 1 1 1 0 0 1 0 1
this is
1 1 0
and this is 1, 1.
1
And you write this
0
as
0 0.
so this is a okay. I am preparing excitation table. Okay, in that excitation table, so how I am writing this? Just observe this. Present state, next state. Okay, and there are some 3 JK flip-flops are there. So J0, K0 condition you have to observe based on this. You have to tick this. 0 has become 1. What is this I can write here? J0, K0. 0 has
1 egg.
1 x, right? Or yes, 1 cross. Then you just see this, only this complete column, Q0 and Q0 dash. So this is 1 and this is 0. Again,
Cross 1.
cross 1. Okay. Then 0 has become 1. Same, right? 1 cross.
Cross.
So now
Cross 1.
1, 0. So you get all these things just like this. Okay. So cross 1, 1 cross, cross 1, 1 cross, like this you are getting. Okay. Cross 1, 1 cross. Okay, I'm not just so based on this you have to observe. I am saying. So 0 has become 1, 1 has become 0, 0 has become 1. Based on that, you are getting these things. Okay, you got this J. So now you know how to write the expression for K0. Can't you write the expression in terms of K-map this by using K-map? You can make use of these don't cares and ones and put them in a K-map, 3 variable K-map, and find the expression for this. That you can find in this way. Okay, suppose this is there. How do you find out this? Okay, K0 means you can take this 3 variable K-map like this. You can put okay here. So this is 0, 1, 2, 3, 4 like that up to 7, right? Just observe that. Okay, so put this when term. So whenever are there, just everywhere you will get 1, don't get 1, don't get like that. Okay, then you can write this as Q0, K0 is equal to 1. If everything is filled, then you can put that as 1. And similarly, you can put J0 is equal to 1. So you will get the expression for like this. Okay. Similarly, J1 expression, suppose you may get like this. Q0, here you have to mention this as not Q1, Q2. Okay. How to explain to you this? Meanwhile, okay, I have given some inputs, right? So can you find out the expressions for J naught in terms of Q naught Q1 J1, okay, J naught K naught J1 K1, okay. Similarly J2 K2 expressions I want, please find here. J2 K2 expressions in
J
terms
naught
of
K
Q
to 1.
naught, tell me.
J naught K naught is equals to 1.
Is equal to 1, right? Then J1 is equal to
Q naught.
Q naught. Check it properly. Otherwise, any small problem is there, I will show you.
They also cannot.
J naught K naught. K1 K1 is Q naught, ma'am.
J1 K1 is equal to Q naught, right? This is also Q naught. We are saying. Then J2
Q1
Q1 cannot, Q1 cannot.
Q1
Q naught. J2 K2 is equals to Q1 Q naught, ma'am.
J2 Q2 is equal to
Q1 Q naught.
K2 is equal to Q naught, huh?
J2 is equals to Q1 Q naught. K2 is equals to Q1 Q naught.
Very good. So this is Q naught Q1, right? These are the expressions you got. Okay, thank you for helping me. Now, what you do, so here J naught is equal to 1, K naught is equal to 1, right? So simply I can keep them here and short. J naught is equal to K naught is equal to 1, and J1 is equal to K1 is equal to Q, right? Q naught. And then this will do 1. J2 is equal to J2 is equal to J2 K2 is equal to Q1 Q naught, right? K2 is also same. Okay. Then you can do this. Simply how do you design now? So this is important step. Okay. So you have to take JK flip-flops, 3 JK flip-flops. Okay. You draw properly. I use one pencil. So here JK. What is this JK? This is also important. J naught K naught, right? Mention this clearly. This is J1 K1. This is J2 K2. This is Q naught and this is Q1. This is Q2. Okay. So now based on this, that means we can initially connect this to the logic high. J1, K naught, K naught. Both are 1 now. So that's why I am connecting this to logic high. Clock signal should be given to all the flip-flops at a time. New clock signal. This is a synchronous counter. That's why this is very important for us. Okay, in clock signal, how I have given? Clock signal is given to all the flip-flops at a time. Okay, so this is important. And initially, anyhow, you will give the clear signal. Okay, so here is made high, later we put that to 0, that is also fine. Then, so based on this you have to plan. J naught is equal to K naught is equal to 1. That is over. Then J1, K1 is equal to Q naught. Simply you can connect this J1, K1. Okay, based on those expressions you have to design this. So J1, K1 is equal to Q naught. So you can just short them. So later J2 is equal to Q1, Q naught. That means, so you extend this Q naught and Q1, extend this Q1, okay. Connect this to the J2. Means what gate I can use here? They just tell me.
And get.
I can use one AND gate here, and that will be connected properly. Okay, so use this and connect to the AND gate. So this is your Q1. This is your Q1. This is your Q naught. So this is connected to the J2. Okay. So you leave this. And if you take this, if you extend these lines, this is Q naught, this is Q1, this is Q2. And if you connect them to the LEDs, okay, output indicators, so you can able to see the counting sequence. Okay, it can count from 0, 0, 2. Where it can count from 0, 0 to here. So this much logic is required for the design of asynchronous counter. Okay, now I'll give you one random sequence. Okay, suppose design, just take the question, design asynchronous counter, asynchronous counter, design asynchronous counter using design asynchronous counter using simple T flip-flops. And with to count the following random sequence. The following random sequence. Random sequence means 0, 1, 3, 5, like that I gave you. Then how do you take this? So what is the first step I said to you?
Flip-flops.
So present state, we have to prepare the excitation table, right? Okay? 1, 3, 5 are there. So you can think of that. Then maybe this may be module counter. Okay? Maybe 3 flip-flops are required, right? Then present state, next state you prepare. Okay? And you have to prepare J0, K0. All of you take this seriously and note down this. J1, K1, J2, K2. How to prepare this I am asking, right? This is not JK. This is only with the T flip-flops, right? So then with T flip-flops means simply, okay, what I can write here, just tell me.
Data.
That's it, right? So here, what is the present state for this 0 means you can take this as 0, 0. 1 means you can take this as 0, 1. 3 is 0, 1, 1. 5 is 1, 0, 1, right? What is the next state for this means simply you can write this as 0, 0, 1. And this is 0, 1, 1. This is 1, 0, 0. And this is 0. Okay, so now for this 0, 1 condition, when it is possible, when t is equal to, when t is equal to 1 only it is possible, no? When t is equal to 1, we get the complement of the previous output, 0 becomes 1. When t is equal to 0, just change the present, 0 becomes 0. you have to do this. Okay. So when P input is equal to 1, the previous output is 0 means that will become 1. Toggle condition occurs. Just remember in this case. Okay. When T input is equal to 0, nothing is changing. 0, 0 only. So that's why 0 has become 1. This is 1. And 1, 1. No change, right? And that will be 0. 1, 0 means this is 1. This 1, 0 means this is 1. You understand or not?
Yes, ma'am.
In block. Okay. So what I am saying, this is the sequence. This sequence we have to read 0, 1, 3, 5. So for that, so I'm asking you to implement using T flip flops. For the T flip flop, just truth table, just observe like okay, T input. Okay, whatever we have now, just observe this. So this is equal to clock. This is the output. When it is 0, okay, but the previous output, assume that previous output is 0 means the same output you will get. No change condition. Okay, when T input is equal to 1, okay, previous output is 0 means you will get 1. If this is 1, the previous output is 1 means it will be 0. So that's what I am saying. If T input is equal to 0, nothing is changing, no change condition I am saying. So that's why here this is 1 and this is also 1. Nothing is changed. That's why I put this as 0. 0 has become 1. This is 1. This is 1 like this I wrote. Now you please tell me for T1. Okay, I am mentioning here this is 0, Q1, Q2, this is 1. Okay. So you can put like this. Okay. Just observe this. For 0, 0 condition, 0. 0, 1 condition, 1. This is 1, 0 condition, double condition. This is no change condition. And similarly for all zeros, this is no change. No change. And this 0 has become 1 means this is 1. 1 has become means this is 1 condition. Based on this, you have to prepare truth table. Okay. Using K-map, you can write the expressions in terms of this Q naught, in terms of this, not this. Okay. So you can easily write them. Suppose 1 is there. If you simply, you can able to simplify this. Okay. Using K-map, you have to write the expression for T naught, T1, T2 in terms of this. Should we stop here, Sharmila? I'll stop. In 2 minutes, I will write. It's very easy. Don't get complexity in this. Okay, just to try to put your effort. Sometimes it is not possible to display this like this non-plan mode. Okay, suppose otherwise if it is a board, I would have drawn properly and explained you everything clearly. Okay, synchronous counter design is very simple. I will send you one link. Whatever are already prepared in WebEx, I have taught to my students. The same link I will share with you all. Okay, thank you for sparing your valuable time. Okay, bye. Did you understand this or not? Little bit at least.
Yes, ma'am.
Okay, we'll stop here. We'll have to go for lunch, no? Bye.
Thank you. Bye.
you can leave now.
Thank you, ma'am.
If you have any doubt, you can ask, ma'am.
Just wait a moment. Sir, HOD sir.
Sir, నేను
Okay, madam.
and one more thing, I'll keep feedback link in the message group. I'll share feedback link also. If you have any doubt, you can ask, ma'am. Anyone.
Ma'am, in last question, the 4 leading states are don't care states, ma'am. Means in KMAP we can keep them as don't care, ma'am.
Yes. You can use them and don't care. Wherever we can able to form octet or quad, there you can make use of them and write the expressions in terms of Q0, Q1. So suppose, for example, here, see this, you are making use of this, suppose anything, suppose 4 input or anything. Okay, so you have got this like this two case, and here it is one. You can form, and this is Q0, Q1, Q2, Q3. Okay, and you are writing the expression for J0.
Ma'am, screenshot.
Tell me. So you can form quad and write the expression for that, I am saying. So you know the basics of this K-maps and all, no? Use both sides 3 code, okay? So that you can easily write the expression for this. Now you just tell me what is the expression in terms of Q0. So that J0 expression is equal to, simply here you can remove, this is Q2 bar, okay? And here you can write this as, this is 1110, right? Okay. So
Rama madam,
this is
your screen is not being shared. So
very extremely okay. I stopped sharing. Okay. Just observe that screen. Okay. I'm sharing that. Just observe this. Suppose you are writing the expression J0, then use this 4 variable K-map and mention like this. So only one is there. You can make use of the don't care and write the expressions for that. So for this J0, you can see this. No, this is a Q2 bar, and what is that Q1 bar? This Q0 bar you can get here. So J0 is equal to Q2 bar and Q0 bar. So use them in that counter. So wherever this Q2 bar, Q0 bar are there, you can sometimes you can add AND gate or any inverter circuit and connect all the flip flops like this, and you can complete the circuit. Any doubt? Counter circuit is very simple, and where we can use, even if you know the basics of this, you can design, you can write a VHDL code also. In future it is very useful for you. So based on this you can write codes.
For
Logic is very,
in JNT syllabus only Verilog is there. VHDL is not there.
even very long also the fundamentals are this, no? That's very used.
Exam there are that.
Okay, Ramu Sharmila,
Much
let
thank
us
you.
close the Bye. Let them go now on the screen.
Okay, everyone please you can leave because you're having lab in the afternoon. Some of are having classes and labs in the afternoon. Please have your lunch and again join for the next classes.
Yes, ma'am.
You can continue. Just in the session.
Yeah, okay.
Thank you, ma'am, for sharing your knowledge and experience to all of us. I would like to hand over the session to Nitika for vote of thanks.
I, Nikita, on behalf of IIT ISF BBIT, would like to thank the students who turned up in a good number. We also wish to express our gratitude to our management, principals, board of directors, HOD, faculty coordinators, and faculty for providing encouragement and support at every instant. Once again, I thank you all for your kind cooperation and for being patient till the end. We, the team of IIT ISF BBIT, are coming up with a few more innovative and informative events ahead for you to enlarge your knowledge. Follow our Instagram and Facebook pages mentioned for more updates. Thank you all.
Okay, thank you all.
Okay, ma'am. Thank you very much. Ma'am, shall I end the meeting?
Yeah, okay.
Thank you, ma'am.
Thank you, ma'am.